Welcome back to the Comsol Tumor Ablation Probe tutorial that I've been doing. On the last video, we did the material and physics both because the materials didn't take very long to go through, so I decided to go through the physics too. And what we are going to do in this video is we are going to build our mesh, go over the study, and I believe we will have enough time to go all the way through the results and export the graph that we want to do. So first things first, what is a mesh? It is a group of geometries. In this case, it's going to be a bunch of triangles that decide where the values for the model are interpreted, or solved is the better word. So let's start by looking at the mesh. There's not very many options here. What we could do is we could do a user-controlled mesh, and we could control our sizes, our element sizes, and the growth rate, and all kinds of properties. But we aren't going to do that in this video. We are just going to do a physics-controlled mesh because this is a beginner tutorial, and I don't want to get too deep into that. So what we're going to do is make just a normal element size mesh, and we're going to build it right here. And as you see, we have a bunch of triangles in our geometry now. So how this works is that you have your initial values here in the probe on the boundaries. And what's going to happen is those values are going to go into this material, and it's going to use the properties of the material to decide what the new values will be at each boundary in these triangles. At each of these boundaries, it's going to solve an equation, and it's going to decide what the value is here. And when it solves that equation, it sends it to the next boundaries, and it solves the equation there. So, and so on and so forth, and it solves the equation throughout the entire geometry. So why mesh size is important is because it changes your values throughout the entire geometry. If you have a very fine mesh size, or no, in a very coarse mesh size, more like it, like this, you aren't going to be getting good data on the fringes because because you aren't solving the equation for a long distance, so it's going to be less accurate. If you have a very fine mesh size, you know, you're going to have good, you're going to have the equation be solved more often, but the computing time is going to take significantly longer. So typically, for like a very important model for research, or if you're going to be publishing your findings, you want to do a mesh size analysis and ensure that that the mesh size is not making your model less valid. Basically, you want to ensure that if you had a finer mesh, having a finer mesh is not going to make a difference, that you have the optimum mesh size, pretty much. So that's your mesh. All you do is build your mesh. We're just going to use this normal mesh. And we're doing a time-dependent study, so it's going to solve all of these boundaries for each time period. And we don't, this model is going to take minutes. So we want minutes, and we want it to be a step size of 1 to 10 minutes. So this range, the first number is the beginning. If I wanted to start at 3 minutes, I would make it 3, and the next is the step size. How large of a step size you want, and then the final number is your maximum value. You can make it go for as long as you want, but beware. Let's say if I made this 1,000 minutes, that computing time is going to take a very long time. And it's also, like, depending on your computer, especially in my situation, because I am using I am projecting the school's computer onto my laptop, that it could crash your system if it takes too much RAM or time. So you want to optimize these things, because you can also find yourself running the same simulation over and over again, and you don't want to be wasting time. So typically the probe is inserted into the tumor for 10 minutes. And we're not going to mess with any of the rest of this. Okay, so now we have everything set up, and we're going to compute. And it's not going to take very long. And first thing that we have is our electrical current. This electrical profile looks good. It has, 2.5 millivolts constantly coming out of the probe throughout the entire profile. And the electrical profile is going to be the same, because the initial condition is for the probe to have 2.5 millivolts. But the thing is, we don't care about the electric potential, because 2.5 millivolts is nothing. It is not going to affect these cells in any way. What we want is this. It's the temperature profile. It's what temperature ablation is based on, is applying heat to the tumor to kill the cells. And like I said, we want most of the tumor to be above 45 degrees Celsius. So first thing we see is the fact that, we can easily convert this. You just subtract 273, but from the temperature that we have over here. But we don't really want to. What we want to do is click and go down to the surface and change our units 2 degrees Celsius. And whenever you do something in the results window, hit plot to apply the differences. As we can see, anything that's orange or lighter is 45, is around 45 or higher. So most of the area around the probe is above 45 degrees. Now we could use this to optimize this further, but I'm not going to do that in this video. But you have a good area that is above the required 45 degrees Celsius, and these cells are going to die. Also, in newer versions of Comsol, there is a tissue damage module, but I'm currently not using that, because the students I am doing this for are going to be using this model on Comsol version 5.3, which they will not have access to. But you could determine the tissue damage as well. So what do we want out of this? We have our model, we've solved our model, and what do we want to do? So first thing is, to make things easiest, we're going to go ahead and add this image to export. And what do we want here? Just to just to make things easier, I'm just going to get rid of the axes because we know how big it is. We don't really care to see these axes on our final result. And now we can just go to our final tumor ablation 2. Okay, so now we have it set up the way we want it. You can change things. You could change the background color and all the font size, and you can change a bunch of things. But you can play with this yourself. I'm not going to do that right now. And we can just name this heat map. And now it's set up. I've made this mistake several times. When you go to browse and you hit save, it does not save it to the location. What it does is it has the directory connected to it. But in order to save it to the location, you have to manually export it by clicking here. And it will be on my desktop. But that's not all we want, because this is good and all, but what does this mean? You just have a picture. How do you interpret a picture? What we're going to do now is make a graph, and we're going to compare the heat profile over time at different areas. So we're going to go up here to results, choose our 1D plot group. And in order to make a graph, actually, I did that wrong. I'm going to create a cut point first, which, I mean, I have the 1D plot group. There's no reason to delete it. You can do it in any order, but I want to make a cut point first. 0. We'll just name it 0. We're going to make the coordinate 0, 0. That's going to be the very center of the tumor. And when we plot it, it's going to show us where that point is. Now, let's go ahead and make our other 2 points. I think it's at 1.5. Let me check real quick. Where do we want these? I want them at 1 and 2.5. So not 1.5. I want this one at 1, 0, 1. It's going to be here. And we're going to do another cut point, and we're going to do 2.5. So what this is going to do is this is going to be on the edge. You could make this point anywhere. As long as it's within the range of the model, you'll be able to get some sort of value for this plot. But that is not what we want. What we want is here. Okay, so now we have a 1D plot group. We're going to leave the data set as study solution 1. I will tell you the significance of that in a minute once we start making our graph. So we are going to make a point graph. And instead of from parent, we're going to make it from our plot group. And the default expression is it wants to give us our output in volts, but the voltage is constant, and overall we just don't care about it. So we're going to click on this replace expression drop down here. We're going to go to heat transfer and solids, temperature, and choose temperature. And we want our units to be in degrees Celsius. Parameter time, unit minutes, and we're just going to see how this looks. Boom. We have it starts at 37 degrees Celsius and it goes up and tapers off at 52 degrees. If we made this go for further, it would increase even higher to even higher temperatures. But for now, this is good enough. Oh, 0 graph. Okay. So next, we want to make another point graph, and we want this to come from data set 1. And we're going to do the exact same thing. In degrees Celsius, and we're going to plot that. As you can see, this has now added our second plot point to the same graph. As long as you have the graphs within the same 1D plot group, they will be added to the same graph. If you created a separate 1D plot group, you would create a separate graph. So we're going to make one more point graph, and we're going to make it from our third point. And it's done exactly the same. Should know the drill by now. And there we go. We have our we have a graph. But there is an issue is what's what? We don't know. So we're going to show the legends on all of them. Go down, click show legends. But I mean, what did these numbers mean? So go to manual and just name them what you want to. Manual 1cm. 2.5 cm. Okay, so now we have a working legend that looks pretty good. You know, maybe the names aren't optimal, but you can name them whatever you want. But there's also another problem. We know that, you know, we can see both sides of this line, but the legend is still in the way. We can't. This is a crucial point. You know, 7 minutes. Someone asked us, we wouldn't know because the legend's in the way. So what you do is you go to your 1D plot group, and you can just change where your legend is. Now it's in the upper left, and it's completely out of the way. And you know, there are so many ways that you can play with this. You can make 2 y-axes. You can flip the x and y axes, which I don't like the way that looks, but for some data, it's very possible that it would be better. You can change your axis limits. What I think it looks good here. You can make it into log scale. You know, there are so many ways you can play with the graph in Comsol. Like I'm not going to go over it, but there are ways to extrapolate your data to a table, and then you can send it to Excel, and you can do stuff that way. But there are a lot of tools in Comsol itself to make a good graph. So what we're going to do is add this to export. We're going to call this 3.what? And I'm going to name this 3. And for this one, we want our axes. What we don't want is our title, because our title, just says point graph, temperature, degrees C 3 times. That's not helpful. So export it. And I exported these to our desktop, and it did, wait, how did it do this? Oh, I chose the wrong one. This is from a previous trial. Here, uh, you can see it doesn't have your axes. It has everything you want. And this has everything you want as well, and it doesn't have the annoying title that we had earlier. So that's all the data that we want from this, and I hope you learned something and can do this on your own, and maybe just help with using Comsol in general is the goal here. And hopefully it was helpful. And thank you very much for watching. You have a great day.